This presentation is delivered by the Stanford Center for Professional Development.
I think we're on. Well, today we're going to do, last time we finished up a bunch of abstract stuff about decomposition, but today we're just going to look at two or a handful of applications in detail to see how decomposition actually works, or where it's actually applied. So the first one we're going to do is rate control in a network. Actually, this is sort of a big topic right now. So if you were to look at this stuff, you would, if you were to go to Google or something, you'd find zillions of papers on this topic. Wow, is that bounce in your, what's that? Oh, it's good for you. Okay, so this, the monitor was just confusing me. That's okay. Okay, so let's just jump in and look at rate control. So rate control, this is the very, very basic problem. So it's non-dynamic. It's completely static here. So the question is, how do you assign rates to a bunch of flows in a network? So here's the way it's going to work. We're going to have n flows. The route's fixed, and they're not going to be split. Although that's, as you'll see in a minute, it's going to work. It'd be fine to do multicast or anything like that. Even split flows, all sorts of other things. But this is just to make it simple. Anyway, once you understand how to do this, you can understand how to do all these extensions. So the variables are going to be the flow rates on a different flow. And then each flow rate is going to be associated with a concave and increasing utility function. So that tells you how much benefit you derive from flowing at a given rate. These could be all sorts of things, the utilities, and I'll talk about them in a minute. The traffic on a link is the sum of the flows that pass through it. So if you have, so these are flows, they flow on links, and multiple flows go through the same link. You add up all the flows on that link, and that gives you the total traffic. The topology of the network is given by a routing matrix. So Rij is 1 if flow j, that's the second index, passes over link I, and 0. And the link capacity constraint is that the traffic, this is the vector of traffic on the links, has to be less than the capacities of the links. So this is the limited resource right here, is the link, the edge capacity. By the way, once you understand this, you realize that this exact framework here will instantly do multicast. So in other words, if you have a flow that passes over a bunch of links, splits, and then goes out to a tree, which would be the multicast thing, this handles it instantly. It'll also do split flows too if you care about it. You could do things like put a number less than 1 here. None of this matters. Okay. So here's the rate control problem, is you want to maximize the total utility derived by running the flows. That's going to be this, and that's separable, subject to respecting the traffic, the capacity limits on your edges. So that's the picture. It's a convex problem, obviously, because this is concave, and this is a set of linear inequalities. So it's obviously a convex problem. And in fact, the interesting part is here, since we're taking the objective is completely separable. In fact, that's the hint. In fact, the thing, when you look at a problem, the things that should light up the part of your brain that's associated with detecting structure, but by the way, you'll see it's the same part of your brain that does structure as does targets for decentralization. So let me just ask a couple questions for fun here. If you were to solve this by an interior point method, how would that go? And I just want roughly how would you write an interior point method to solve that? Let's talk about the objective. What does the Hessian of the objective look like? Block?
Block diagonal.
Why block? Yes, there's scalars.
Oh, sorry.
So diagonal is diagonal. So that should get your attention instantly. And why? Because it's separable. Okay, so immediately you should look at this, and separability should light up two parts of your brain, the part associated with decomposition, but they're really the same part of the brain. After a while, you put them in the same. And the other part is structure in the Hessian. So the Hessian's diagonal. And of course, whether they're coupled by the constraints, right? So what that should do when you see something like that, where it's the objective is separable, but they're coupled only by the constraints, is things like dual decomposition, primal decomposition just come to mind like immediately. So, okay, so let's look at dual decomposition. So this would you'd form a Lagrangian. So here you form a Lagrangian, and what we're going to do is there's two ways to do maximization problems. One is to keep in mind everything switches, or you can put a minus sign in front and make it a minimization problem. So I guess that's what's done here. So the Lagrangian for minimizing minus u is it's minus u, the objective, plus lambda transpose RF minus c, and these are going to be positive here. Now, of course, when you do this, a very cool thing happens. You write this as R transpose lambda quantity transpose F. That's this thing here. That's at least the jth row of that. Minus, and then you have this minus c. That comes out over here. So here, these lambdas are associated with each link capacity constraint. So lambda 4 is associated with the fourth link and the capacity constraint. And in fact, we're going to see, well, it's going to be clear anyway, but we're going to associate lambda I with a price per unit flow. So it's a tariff or a rate. It's a price rate for using that link. And then in fact, we can actually interpret all sorts of other stuff as this. Rj transpose lambda, R is a matrix that has a 0 and 1 and tells you what links connect into which. So R looks like this. It's got here, these are the flows. And then here you have zeros and ones like this to tell you if this is link 1, this row, and then it's got ones in the entries if that flow passes over that link. So that's this is that. This is R. And if you look at R transpose lambda, it basically says now you're sort of, well, you just transpose this thing and you go down a column instead of a row. If you look at a row here, you're looking at a link. And the ones tell you which flows are on that link. If you look down a column, this tells you exactly, it tells you a flow, actually, because, for example, the first column is a bunch of ones, and this gives you the first flow. It tells, this is the list of links that flow over, that flow 1 goes over. So that's what this column is. And if you take this column transposed lambda, that's actually a beautiful thing. It's exactly the sum of the lambdas over the route taken by that flow. So by the way, the routes, those lambdas then have an interpretation of a cost. So let's, sorry, a rate. And then you can even interpret this beautifully. This right here, this thing, that's actually the total rate, because if you go over a link that costs you whatever it is, $1 per whatever per flow rate per megabit per second, and you flow over another one that's $2, another one that's 50 cents or whatever, then altogether that's like $3.50 per megabyte per second or whatever, megabit per second or whatever it is. That's what this thing is. So this is actually that is the total tariff per flow rate on that route. You multiply by this. So this is as if you're charged by these carriers to carry your traffic. That's what this is. This is, of course, the negative utility. Or if you want, you could flip the sign on it and say it's the utility minus this, and then it makes perfect sense. This is the amount of utility you derive from having a flow rate Fj. And this is the net utility, because you subtract off the cost of running your flow over all those edges. Okay? So this idea of the lambdas being prices, it's obvious for anything, but I mean, that's exactly what it is. And this is negative net utility. Actually, I want to back up and before I go into this, I did want to mention a few things like what the rate functions might look like. The rate, sorry, not the rate functions, the utilities. So let me just say a little bit about that. They have to be concave and increasing. So here's your flow, and then here's your utility, like that. Simplest utilities are something like this. That basically tells you something like, it violates, we're assuming here u is strictly concave, but let's just ignore that for the moment. This utility just says the more flow you get, the happier you are. And getting another, whatever, 10 kilobits per second, even when you've already got a lot, makes you just as happy as the first 10 kilobits per second, something like that. So here there's no satiation effect, right? So you don't, the marginal utility of additional flow is constant here, right? So that's this one. This, by the way, might be a good model if that flow represents sort of email or something where you're just paid by the amount of stuff that kind of goes through. The more, the better. That's this thing. But you can have all sorts of other things. You can have this. That's a very interesting utility. What does this utility say? I mean, this basically goes up to some f0. You're happy if you go up to f0. And then above that, it doesn't matter to you. I mean, and of course, you can do lots of other things. You can do things like this. Right? That's a good one. That says, this basically, with a utility like this, you're basically saying, look, the more flow I have, the happier. I really appreciate flow at whatever this slope is, up to some amount of flow here. At this point, I sort of get sated, and I'm happy. And this says I'm still happy with more, but the marginal utility goes down. Okay, so this is one picture. You can also do this. You can have something that goes to minus infinity like that, and that says I will get infinitely unhappy if you fail to provide me with a minimum flow. Actually, this is kind of stupid because if you have a minimum flow on a flow here, remove it and just decrement the capacities of all links it goes over, and the problem remains the same. But still, this is the idea. So these are pictures of flows. Here are some ones that people use that are very common. One is a log. That's extremely common, a log utility. And this would come up in networking, all sorts of other areas. And what's interesting about this one is it says basically what's equally attractive to you is a percentage increase in flow. So every time the flow you get goes up by 10%, it makes you equally happy. So that's going from 1 kilobit a second to 1100 bits per second, 1 megabit per second to 1.1 megabits per second, equally happy. That's log. And there's all sorts of other things in between, square roots and all sorts of other stuff. So that's the picture on the utility. Okay. I just wanted to mention that. Okay. So here's our Lagrangian. This is a Lagrangian. And the thing to notice about the Lagrangian now is this thing is separable. And of course, when this is linear here, and this will work for linear constraints, of course. Whenever you have linear constraints and you make a Lagrangian, everything splits. So you have perfect. This is completely separable. If I ask you to minimize this over the vector f, it can be done at each flow completely independently. Can optimize itself because it's a sum of functions of the individual flow rates, and therefore it can be done completely separable. Okay. And it's actually quite interesting. If you think about what actually happens when each flow minimizes this function or maximizes uj minus that's the net utility, is you're basically doing this. You're publishing prices on all the edges, on all the links. So this link has or tariffs or whatever you want to call it. You're publishing prices on the links. And then you tell each flow, you know what, don't worry about the link capacities, but charge yourself actually really or fictitiously a certain amount for your flow rate on every link. And then just optimize your net flow. And that's how this works. So we'll get to these. So the dual is easy to work out. You just you minimize this over each fj. That's a single variable problem here. And of course, you can write this. You recognize it. It's a minimum of a convex function plus another thing. And that can be written in terms of in terms of a conjugate function easily. So it's negative uj, that's a conjugate function. That's of course that's the conjugate. That's convex. That's the conjugate of it. And it's evaluated at minus rj transpose lambda. So you get this. And the point is, this is just this is now this thing here. I mean, these things are just scalar functions. Okay, so you get the following dual rate control problem. And actually the interesting part is the primal rate control is from the point of view of the users. Basically says calculate flows that will satisfy, that won't violate the resources available on the network. That's the link edge, the edge capacities. And make sort of the sum of the happiness of everyone operating on the network maximized. The dual problem is this one. And the variables actually are the link prices. So the dual problem, I mean, this is often the way it works with primals and duals, as you know now. The dual problem actually takes the other point of view. So you could argue that the dual problem is actually the one faced by whoever's operating the network. Because basically the dual problem involves prices, and it says how should the network price the link flow, all the links. You're going to price them, and you're going to price them so that actually everyone else is going to back off, so the users are going to back off, and you'll utilize the, and come in under, if you adjust your prices right, they'll come in under the capacity. So here, these are to be interpreted as link capacities. This is a pricing problem. And what you want to do is you want to price the whole thing in such a way that you minimize the net the net happiness. It sounds kind of evil, but anyway, but that's actually exactly what this is. So, oh well. So, all right. How do you get a subgradient of the negative of this, which is, I guess, lambda transpose C plus that? How do you get a negative of this? It's very simple. It's stuff we've looked at now several times. It's this. If you have a flow, you have some lambdas, you evaluate the optimal flow under this pricing. Optimal means that flow it optimizes its net utility. That's Fj here, and you optimize this. Then you go back here and you look simply at Rf bar. That's the actual traffic on the network minus C. And that is in the, that's an element of the subgradient that's in the subgradient set for this dual function here, the negative dual. So that's what that is. So, and actually this makes perfect sense. This thing here is actually the traffic violation or something. If it's positive, it basically says that the pricing, it tells, well, if it's positive, it tells you that the subgradient of this thing, it says that if you increase the price, something's going to, I guess, whatever it is, it has the right sign. It's all mixed up now because I'm maximizing and minimizing and switched it all around the middle. But okay, that's the picture. I should add, by the way, if G is strictly convex and differentiable, sorry, if the U's are, this is actually differentiable. But I'll still write this because then I'm going to cover cases like where you have kinks in the utility. So, by the way, if you have a kinked utility that goes up linearly and then transitions to a new slope, what do you think the optimal solutions are going to look like? What do you think is going to happen? What would you expect when you solve a utility on a network, and the utility looks like this, like that? Let's just suppose that's 1. What do you think?
It's going to be bunched up, or the derivative is discontinuous?
Yeah, where else are they going to be bunched up? 0. Yeah. Look, there's this is like your old friend the L1 or the exact penalty type thing here, and then that's another kink. And so in fact, if you optimize a network with whatever 10,000 flows and 50,000 edges, when all the smoke clears, we expect the following to be true. A bunch of flows will be sitting right at 1. Okay? Some might be sort of out here, because there might be some light traffic areas where it's not really congested. If there's if a flow goes through a really congested areas or multiple really congested areas, what do you think that optimal flow is going to be? What do you think? 0. Yeah, that's this thing. So that's exactly. And by the way, if that happens, then you can go back and brag and say things like, "Wow, I'm using convex optimization to do admission control," because that's actually admission. That if the optimal flow rate is 0, it says actually any amount of flow I allocate to you will lead to a decrease in the total, in the public good. That's the sum of the utilities. You're too expensive. And that would be a flow, of course, that goes through, if you go through a whole bunch of congested areas, then you're not worth admitting to the network. So that's admission control.
Does it have to do that it's a linear program?
Hmm?
Does it have to do with the fact that it's a linear program?
No. It has to do with the fact that the slope here is fine. So if I did this like that, and then and these are both curved, right? It has to do with the non-differentiability here and here. So this could be like x to the 0.8 over here, and then this could transition to x to the 0.5. You'll get exactly the same thing. So it's the kink that matters there. Okay. Okay, so here's dual decomposition rate control. It works like this. You start with an initial link price vector. So, for example, you just say, look, everybody is a dollar per megabit per second. You just initialize that way. It doesn't make any difference. Then it says each route, you sum the link prices along the route. That's calculating this thing. And then that's the total price on flow J. So each flow walks along, you can even imagine some protocol for this. I mean, this is obviously not how real flow control protocols work, but actually a lot of people have done a lot of work on back interpreting real flow control protocols, as in TCP/IP, back to this framework. But nevertheless, you can imagine a protocol where you go along you flow along the thing, and as your packet moves through across each link, somebody like the operator goes into the header somewhere, finds a price, and then increments it by its price. Then it gets to the end, and then when it returns, you look at the header, and it tells you the total price on that on that route. Okay, so this says collect the prices on the routes. And then it says you optimize the flows completely separately using flow. So this is completely independent. So every flow just independently optimizes itself. And what it does is it maximizes what it really wants. That's this utility. Minus, and then it has, this is either a fictitious or you can think of it as fictitious, or it could absolutely be a real charge. And it subtracts the charge for using F. That's what this is. This makes perfect sense. Let's see. What would happen here if one of these were 0? What's the FJ then? What? Oh no, just plus infinity. It's like no problem. These are increasing, right? And these are increasing, and if it's costless, you'll just say, oh, not a problem, and you'll open up your flow control. You'll open up your valve to the widest thing it can be. So, what's that?
Are the routers, when they make a decision of which way to send the packet?
Nope. Right in this, the problem we're looking at right now, the topology completely fixed. The routes are not changing. The next thing we're going to look at is going to do exactly that. Could you combine them? Yes. Once you get the idea on these things, you can solve any of these problems. Right. So no, routes are absolutely fixed. Okay. Everybody got this? So that's the picture. Oh, by the way, there's no reason to believe that when you set the flows this way, your link capacities will be respected. Although there's some obvious things you can say. Let me ask you this. What if you get this to step 3? Step 3 says these are basically flows calculated with no direct knowledge of link capacities. It doesn't tell you whether you're over or under or anything like that. It says that's the price. Please deal with it. Please crank your flow up until the marginal utility you get is equal to the price. That's actually all you're doing, is you're getting U prime equals lambda J. Then you calculate this, and then let's actually just figure out some things here intuitively. If S turns out to be quite positive, what does it mean? If the slack on the link capacities is they're all positive and they're all substantial, what does it mean? What does it mean?
Lower the prices.
It means that the flows are not large enough. The flows are not large enough because the prices are too high. So it basically, you told them some ridiculous price, they all said, ooh, that's expensive, and they all backed off to some slow rate, so they're just dribbling stuff down the network, and you're way underutilized. Okay? So, in fact, if this is positive, it says that the prices should be lowered, and, good, okay. By the way, it's a 300 level class. If the signs came out wrong, wouldn't bother me in the slightest. That's your homework to figure out, but the story still goes. All right, so in this case, what would happen is this is a dual subgradient update. It says take the old prices, subtract from that some positive multiple of the current slacks, and then you take the plus part of that. Right. By the way, can a link charge, a lambda, can it become 0? If this becomes negative and you take the plus part, one of these becomes 0. Is there a pathology there? What happens if, can you have well, that's a good question. When you solve the optimal flow problem, can an optimal lambda be 0?
Well, there's no flow that needs to go over that way.
Yeah, sure, okay, no flow. Any other cases?
If you're ready to pay people to use it.
No, we're not allowed to do that. Lambda is going to be positive. Yeah, when would that happen?
When their dividend function is 0 at this ending.
Oh, you mean flattens out? No, okay. It's just simple. If at the optimal flow solution, that link capacity has positive slack, then the optimal Lagrange multiplier is 0, right? That's all it is. It just tells you that. So how could you get a link that is how do you get a link? In fact, someone tell me, what's the simplest case? Show me a case where a link capacity is not active at the optimum. It doesn't sound right? Because the more flow you get, the more, but can someone give me an example?
It can happen if one link with a high capacity is surrounded by links of low capacity.
There you go. So just here, I mean, it's a perfect example is just the simplest one. I mean, your example was exactly right? But here's the simplest one. The simplest one would be this. 2 links, like that. This one has a capacity of 10, and this one has a capacity of 1. And there's just one flow, like that. Done. So obviously, the optimal flow is 1 here. I don't care what the utility is as long as it's increasing. Optimal utility is 1. And so the link capacity here is never active. And therefore, the Lagrange multiplier on this one is going to end up being 0. And it's going to be completely determined by this one. Okay? So that's the picture. Okay. All right, so this is so these are fun. It's like all dual decomposition algorithms. They always fit a story. In other words, you could explain this to someone, you could explain this to undergraduates, you could probably explain it to you could explain this to high school students easily. And then you might ask, so why did you sit through 364 and various other classes to get here? What would I say? I'd say you know more, you have a more sophisticated view, or there'd be no reason to believe that this method would work, or something like that, and now you know otherwise. You know that it would work. So, okay. Is that really worth sitting through all those classes? I'll have to think about that. I'll get back to you on that. Yeah.
So I'm just interested to see, is it possible to have a price update that is multiplicative rather than...
Yes, it is. Yeah. So I'm showing you the simplest possible dual decomposition method, just straight subgradient. Okay? You could do all sorts of others. You could do a 2-term recursion and update lambda depending on not just the current thing, but the last one. These things would immediately work much better. And in fact, for this particular problem, a lot of people have looked at you take you write the lambdas as the exp of some other variables, and you update those. And that leads to a multiplicative update. So, yeah. Okay. Let's see. And I'm just trying to think, there is like one minor hole in this, but it doesn't matter. I mean, what could happen is if I started with a too high step size here, then here's what would happen. If you start with lambda large and alpha k large, lambda's large, so what's going to happen is you're going to be way underflowing. your surplus is going to be high. But alpha is large, so it means that in your next step, all lambdas are going to go to 0, and now everybody goes insane at the next step, because everybody says, sorry, it's costless on my whole route, not a problem, and you open up your pipe to the maximum rate. So, that's the only sort of hole in it. But I'm not going to do all the details to fix that. You can do all sorts of things there, limited it. You could put upper bounds on the flows or whatever. Doesn't matter. Okay, so that's it. It's actually quite beautiful method. And you can see this is very far from the silly little things we were looking at before, where you had the two, you sort of had like the two problems and the two subunits of a firm, and they're sort of setting the prices and then each optimizing separately. This decentralizes across huge, vast things. I might add that things like this can actually be done and actually are done. I have to fix that someday. I'll do it. Okay. So, this is kind of obvious, and I've already emphasized it, but the idea is this is completely decentralized, utterly decentralized. The link only needs to know the flow that passes through them, and the flows only need to know the prices on the links that they go through, right? So you can easily imagine, for example, not that this would do anybody any good, but you can imagine making sort of an object-oriented implementation of all this, where very little information is available to anyone. In fact, each flow needs to know absolutely nothing except what is the current price. What's the sum of the prices on the links it flows over? So a flow doesn't even need to know, for example, how many links it has. Totally irrelevant. It's completely irrelevant, right? All it needs to know is what's the current total price. Each edge does not need to know anything. Doesn't need to know how many other edges there are in the network. Doesn't need to know topology. Doesn't even need to know the IDs on the flows. In fact, doesn't even need to know the flows going through it. It only needs to know how close is it to capacity. That's how decentralized this is. Okay. Now the iterates actually are often infeasible, but in the limit you do have this. So there's lots of ways people sort of deal with this. By the way, there's something that people do that's a bit confusing, but it's widely done. And it works like this. They confuse iterations with actual time. So here, in a subgradient method, the iterations don't have anything, you're not actually flowing at these things. So in fact, probably the best way to conceptualize this is to imagine tiny little packets that have no payload, just like header. And they fly along the route and are tagged. Each edge tags it with a weight. Then it comes back to the process that's going to run the flow. And then each edge is sort of adjusting the price, and this goes back and forth until basically somebody somewhere, I guess there's an all clear thing. Each edge finally says something like, all right, you'll never actually get under capacity, but you'll get close enough. At that point, a little token goes back to every flow that says we're cool and we're good to go, and then you turn on your flow. Everybody see what I'm saying? So that's the right way to conceptualize this. Now, unfortunately, a lot of people imagine the iterations here to actually be done. So basically what happens is at each step you have the things. When you try a step in a subgradient method, it really means pump that flow down that tube. What happens then is actually kind of interesting, and it can be interpreted all via dual decomposition. What happens is this. If you pump too much down a link, in this model, not this one, and I think this is the one that leads to all sorts of very strange and confusing things. If you pump too much flow, what would actually happen in a dynamic situation if I have a link with capacity 1, but I have the total flow going through it actually is like 1.1. What would actually happen in a real network? Well, it depends. Actually, it depends on exactly what the router is or whatever is supposed to do. One thing it could do is just take 10% of the packets and just dump them, just terminate them right there. The other thing is it can push us onto a buffer. And if it pushes onto a buffer, then basically, if you're asking for a flow of 1.1 down a pipe, but it only has a capacity of 1, you pump at 1, and your buffer is growing at a rate of 100,000 whatever packets or bits per second. Everybody see what I'm saying? So then it turns out you can actually go back in that situation, and you get a two-term dual subgradient thing. And there's a whole class of algorithms now in network flow control called back pressure, and that's exactly what this is you look at and actually it's nothing but a dual decomposition method. So, all right. So I think I just confused everybody by warning you that there are interpretations of this that are deeply confusing. So, is anyone not confused? Because I can confuse them separately. Oh, good. Okay. We have stationary point in. Oops. Hello? Am I missing something? No? It's not like 7 pages long, is it? It's not. What? It shouldn't be. Next. What do people think? Okay, let me try one thing then. Well, that's nice. You can see the weather. That's good. It's sunny outside. That's always good to know. Am I missing? Let's just. Did this get truncated?
There's two.
Yeah, there's another one, but that isn't just apps. This one says apps.
Really? Yeah. Okay. I don't know what happened here. No, I thought so. Okay. That's like. I'm sure you know, right? There's several things that scare professors and things like that. That's one of them. The other one is when someone runs up to you and says, "My God, you're teaching in half an hour." And you're like, "I am? What class?" It's like music history. And you're like, "But no, that's a mistake. It's impossible." And they're like, "They're all waiting there." So anyway, this is the other one. Like you walk in with the wrong lecture notes, and it's like 3 pages long. And okay, all right. Here we are. Whoop. Okay, now let's see if everybody's happy. Look at that. Okay, who knows? Okay. All right. Okay, now when you do this, you, as I said, you're not. What's happening is only in the limit do your flows respect the capacity constraints. But there's ways, of course, obviously, to produce a feasible flow if you have to from a proposed flow, and there's tons of ways to do it. One is like you could do proportional back off, and boy, you can imagine a whole industry and thousands of papers to be written on this. And so it would work something like this. You could let eta I be the traffic on the edge divided by the capacity. That, of course, should be less than or equal to 1. But if it's less than 1, it means you're under capacity. If it's bigger than 1, it means you're over capacity. And you could do the following. If someone has if there's a proposed set of flows, that's the current one, and someone says, okay, enough of this silly decomposition nonsense, it's time to actually put some payload in your packets and start flowing, then what you would do is this. I mean, this is a very simple method for generating a feasible flow. It goes like this. You take the flow, and you divide it. You do a proportional back off. You go over all of your links here. If the worst case, this is like the overload factor on your link. You look at so you find the worst overload factor on your flow. By the way, if that's 0.8, that's great news, because it basically then this is actually telling you, please crank your flow up by 0.8, by 1 over 0.8. Sorry, like that. That's what it does. If this is like 3, it means you're way off, that at least one edge is oversubscribed by a factor of 3, and it tells you to back off. So this clearly produces a feasible. That's a feasible flow, totally obvious. And in fact, this is actually a step in primal decomposition for this, but that's often the case in these things. So let's just look at an example and see how this works. So I have 10 flows, 12 links. Now I should add, obviously this is not for that. That's totally obvious. I should also add, just to make sure this is completely clear, is that if you needed to solve a flow problem, with a million flows, 2 million edges, 5 million edges, whatever, by far the best method would be just an interior point method. Period. That's by far the best method. By far. So the whole point about this dual decomposition is that's if you could collect all the data in one place. You'd be way better off doing it that way. The nice part of dual decomposition is it's got all sorts of data hiding, and bits and pieces are encapsulated and all that kind of stuff. So that's the advantage. It's not speed, not quality of solution, nothing else. It's just the decentralization. Okay. All right. So this is just a simple thing. I guess there's 12 links. The link capacitors are chosen randomly, and we'll use the log utility. By the way, if you go to Google and type in log utility network, you'll find tons and tons of stuff. And a lot of it, there's some arguments you can make, like it delivers proportional fairness or something like that to everybody. By the way, if you put log utilities, you don't do admission control, and that's kind of obvious, because the utility associated with denying somebody entry to a network, a flow, setting a flow to 0 in a log utility is minus infinity, which is basically means infinitely uncool, and so it doesn't happen. So everybody gets a little bit in a log utility type thing. So the optimal flow, you can just get a formula for this. It's very, very simple. You put a log minus this, and I don't know what it doesn't. It's a conjugate of the log. I forget what it is, but whatever it is, it's something explicit. And we set all the initial prices to 1. And we'll take a constant step size. Actually, this, of course, would not work, or would work in a limited sense if these things were non-differentiable. It turns out in this case, the dual function is completely differentiable. In which case, what you can say is this. If a constant alpha if it's constant and small enough, you're guaranteed to converge. That's the statement for differentiable, the differentiable case. And in this case, it's differentiable. Okay. So here's an example. These are iterations running, and this shows you the utility derived here by the current thing, and this shows you the this is g of lambda, which is an upper bound on this utility. So that's what's happening, and you can see here that in something like 50, 60 steps, you have you've gotten the utilities about the right way. This is the utilities of the corrected ones where you back off here. This is FEs. So that gives you a primal point, primal feasible, and that gives you a dual feasible point, which is the upside. Okay. Now as you're running, you run a maximum capacity violation. So and that looks something like this. I guess when you first start, there's violations as big as by 1 or something like that. Roughly 0.7 or 0.8. Something like that. Now, all the capacities themselves are between 0.1 and 1, so we can get a scale for this. It says that already by about 20 steps, your capacities are your capacity violations are pretty small. And certainly by the end of this, your capacity violations are 10 times smaller than the smallest capacity edges on the network. So that gives you the rough idea. Okay. So now we're going to do, that's odd. Okay. Something's going on here. That's very odd. Now we're going to do, we'll look at a different problem. And these are just supposed to be just 2 different problems in networks and stuff like that. And actually, you'll see that once you get the ideas, you can do zillions of generalizations of these, and you can combine them and all that kind of stuff. But these are sort of the 2 prototypes of these things. So this single commodity network flow. Single commodity means it's something you should think of a flow or traffic on an arc. A single commodity means that you should think of like electricity, water, gas, diesel fuel, something that's interchangeable, and you don't mind what it is. By the way, in a communication network, a single commodity flow, what would that be? That would be actually just packets all destined for the same place or something like that. That would be a single commodity flow. So it's basically like a sensor collection network. Then you have single commodity flow, something like that. So everything is the same. It's all interchangeable and so on. Okay. What you're given is an external source or sink flow at each node. And the sum of the external sources or sink flows is going to be 0. We'll see in a minute that has to be. And we'll have a node incidence matrix, and that's going to, this is the graph incidence matrix. It just tells you which edge goes into and out of each node. And it's the traditional one where you have the rows give you the edges, and the columns, the column index j gives you the sorry, let's see, did I get that right? No, nodes. It's nodes by edges, like that. So it's node by edges. Flow conservation says this. It's ax plus s is 0. So if you look at ax, the vector, let me just, I shouldn't have to write, let's just write it down though, just to get the picture here. So you've got a bunch of nodes like this, and you have directed edges like that, and then each one has an external flow into it. By the way, these edges do not mean that the flow has to go from one, it's simply a reference direction like in an electrical circuit. So when the edge goes like that, that says that if the flow is actually this way, it's positive. If it goes that way, we're going to call it negative. So it's just like an electrical circuit. You take a branch, you label the arrow, does not mean the current goes that way. That's the reference direction, and it merely means that positive current means you're going that direction, negative current means you're going the other way. Okay. Likewise, these sources that enter the network like this, they represent, they can either be sources or sink depending on the sign. Okay? And if you form AX, are we using X for the flow? Yes, we are. Okay. So if X is the vector of edge flows, AX is a vector, and the height of it is, it's the size of the number of nodes. And AX tells you precisely the violation. It tells you, I'm ignoring these flows. It tells you precisely the net flow at that node, where you add up everybody coming in and you subtract everybody going out and what's left over. If you add in the S, it means that all the flow balances. So you can think of this as the basic conservation equation. This would be the exact same equations in an electrical network. This would be absolutely identical. So here, the X is the current on a branch. S is an external current injected or whatever, and you'd have AX plus S equals 0. In which case, this would be something like, this would be Kirchhoff current law. Okay? And what we're going to do is we're going to have, this of course describes lots and lots of feasible, there's lots of X's that satisfy AX plus S. Well, I mean, not lots, depends on the null space of A, of course. So you get any flow, and then you have a null, something in the null space of A. Oh, by the way, what is an X in the null space of A called? I mean, I'm just asking the English. You can almost guess what it's called. What does it mean to say AX equals 0 in a network like this? What's AX equals 0? What's it mean? Here, I'll draw a picture, and then you can tell me what the null space is. Here, we're going to do a super simple network. It's going to have 2 nodes. What's that? Here. I've got 2 nodes and 2 flows, and I'd like to know what on earth, in this case, what does the null space of A mean? Give me an element in it, and please tell me what it means. What's an element in the null space the way I've drawn it here? Any multiple of 1, 1. Right. Everyone agree? If x1 is equal to x2, AX equals 0, because there's the net flows here is 0, net flow there is 0. So you won't be surprised to find out that the null space of A is actually called, any element in the null space is called a circulation. Right? So in this case, it's a circulating flow. But in the general case, you call it a circulation too. So, by the way, it does not have to be a flow that goes along the path, like something like this. That does not have to be. Actually, those are in the null space. But you could have some weird thing where there's all sorts of positive and negative. Just anything in the null space is called a circulation. Okay. It's just to get the figure, the idea for how all this works. Okay. So there are lots of things in the null space. In fact, the null space, of course, so actually another way to say it is this. Find one feasible X, that's a flow that satisfies your flow requirement, your external flow. And then you're really asking to that, add something in the null space. Right, so actually, how do you optimally add circulation or whatever to that? And what you want to do is you want to minimize a flow cost function. Okay, so, and if you wanted a picture for this, it doesn't really matter. This could be a wireless network, and this could be the power required to support a level of flow. Okay, so in a wireless network, for example, if you say you're transmitting a megabit per second, you calculate on your rate curve what power it takes to do that, and then this would minimize sort of the total power on the network, for example. But that's rough. That's the idea. Okay, so this is single commodity flow network flow setup. Okay, so the network flow problem, the single commodity network flow looks like this. You minimize these separable flows subject to AX plus S is 0, and that's convex, readily solved with standard method. I mean, completely readily solved. We'll see the dual. The dual is going to be quite beautiful. As you won't be surprised, a flow problem here, the dual is going to involve a problem involving potentials. I mean, again, if you know electrical engineering, you would suspect this. I mean, this would hardly be surprising. So we'll see that when we work out the dual variables are going to be potentials at the nodes. And in fact, it's more than that. You're going to find out that all that really matters is the potential difference across each edge. So I'm just saying, you should be prepared for this. It's going to happen. But there's no, I don't mind saying it now. Again, if someone just walks up to you and says, solve this problem, and there's nothing else here, there's no other reason or excuse for decentralization. By the way, the argument that it's cool, I think, doesn't really work. It is cool, but that doesn't matter. You'd be way better off solving this using a standard method from 364A. So sparse matrix techniques would just beat anything if you could collect the data in one place. Okay. We'll see a decentralized solution. It's going to look different from the flow one, but you'll get the idea. So we form a Lagrangian. That's this separable function of x plus nu transpose ax plus s. And of course, the constraints are linear. So when you form a Lagrangian, everything separates. So this is just completely generic with linear constraints. And now this function here is completely separable in the x's. So why? Because this is separable. It starts that way. And this is linear. Everything linear is separable. Any linear function is separable in all variables. So I said linear functional, and actually that's correct. A linear functional is a linear function that's real valued. So, okay. And that's actually very interesting because this says that if I told you what nu is, these Lagrange multipliers, by the way, the Lagrange multipliers are associated with nodes. The variables are associated with flows on edges, and not surprisingly, the Lagrange multipliers are associated with nodes because this vector has the height of the number of nodes, and in fact, it really tells you the node. This AX plus S is very simple. It's the vector of KCL violations. It's how much are you violating conservation of flow at that node. Okay, so this is associated with nodes, and we'll see that they're potentials. We'll see that very quickly. Okay, so this is completely separable in the x's, and let's actually look at what I want to see what A transpose nu is. So let me try to get that right. That's going to be it's 8. So we go A transpose nu transpose times x. That's the component in the Lagrangian associated with the constraints, the linear component. And the entry, this has various entries, but the entries look like this. It's AI, AJ, transpose, let's see, and that is nu. And the AJs are columns that have a +1 and a -1 in them exactly. And it encodes for the jth edge, the head and the tail node. So that's what AJ is in this. In the A matrix, it looks like this. You've got each column has a +1 in it and somewhere a -1. Everybody else is 0. And that encodes that for this edge, it goes into or out of, I forget what the convention is, one and then out of the other. Okay? This thing is beautiful. This vector is the difference in potentials across that edge. So if I have the jth edge and I form AJ transpose nu, I take this thing and I transpose nu. And it basically, if this is nu k and this is nu L, then AJ transpose nu is nu k minus nu L. So it's quite beautiful. And in fact, you can already see something very, very cool. Notice that the Lagrangian in nu has the property that you can add a constant to all entries of nu and nothing happens. I can add 27 to every entry of nu and the Lagrangian is completely unchanged. Is that true? No. Yes, it is. Sorry, it is. Sorry, yeah, I confused myself momentarily. Let's see. It's obvious in one case, but not in the other. In one case, it's easy. Every one of these, each of those vectors looks like it's got a 1 and a minus 1. If I add 27 to every entry of nu, it makes no effect on that because this is calculating potential differences across an edge. Here the reason it doesn't matter is because S, 1 transpose S is 0. So that's why it doesn't make any difference here. The sum of the S's is 0. Okay. So we'll use the notation delta nu j to denote the potential difference across edge j. So actually these examples are fun anyway because they should kind of be in 364A just because it gives you more, you get to see duality in more sort of applications where you get beautiful interpretations. I mean that's almost always true in duality. Okay, so here's the network flow dual. It looks like this. The dual function is you minimize this Lagrangian. And this is completely separable now because so in fact, for each edge to determine its flow in the Lagrangian, it turns out it needs to know absolutely nothing. It does not need to know actually anything other than the potential at its head and the potential at its tail. Nothing else there's absolutely nothing else you need to do. And you take that potential difference, you multiply by your flow, and you add in your cost for flow and you minimize. And you can write that this way. This is the conjugate of the edge cost. And the dual problem is simply to maximize this G. So that shows you how the primal is a flow problem and the dual is with a conservation constraint at each node. That's what a flow problem is. So I guess that's okay. Then and the dual is one involving assigning nodes to potential. So it's just like the link thing, except the network flow problem, but I mean the rate termination problem, but different twist. Okay, how do you recover the primal from the dual? That's easy. If these are it's easy only if these are strictly convex. Then you get a unique minimizer, xj star of that. And if these are differentiable, you can get, you have just a formula for it. It's very easy. And you get the optimal flows from the optimal potentials. And that looks like this. It just says that xj star is equal to, this is xj, that's the conjugate one. And that's the optimal potentials. Now, by the way, this formula is quite interesting. In electrical circuits, this formula is going to be the nonlinear IV characteristic, the current voltage characteristic, because basically you think of Y here as a voltage potential across an edge. And then as a result, this function here, the inverse of literally the inverse function of the derivative, it's the argmin of this thing. This function here is actually the thing that maps an applied voltage across that edge to the resulting current flow, right? So for example, for a resistor, that's linear, and that actually corresponds to quadratic flow potentials, in which case these are energies. Okay? That's for the electrical analog. If you know what that is, that's fine. And a subgradient of the negative dual function, that's easy. It's actually just this. All the flows totally uncoordinated. There's no reason to believe case you have flow conservation. They look at the potential at their head and their tail. They privately minimize something, which is sort of a net power. They privately minimize that. And then they say, that's my flow. And then basically at each node you look and you find out what is the what is the flow conservation violation? That's this. If that's 0, you're done. That tells you, of course, that G is maximized. If it's not this thing here, the flow conservation residual, otherwise gives you a subgradient. So, okay. So here it is. You do the following. You start with some initial potential vector nu, doesn't matter, and you determine the link flows from the potential differences. So you simply look at you calculate this way. Then you calculate the flow surplus at each node, and we'll call that capital SI. That's the surplus. And then it says you simply update the node potentials. It's actually quite beautiful how it works, and I will change my story to get the sign right, just assuming the sign is right here. So let's try that. So what happens is this. You have, let's make an electrical current. So you're flowing from one node to another. The first thing you do is you calculate the node potential difference, and then you simply flow, you calculate a flow that goes across that. Then if the receiving node turns out to have too much current going in, net current, then it says that potential should go up. Yeah, that's it. That potential should go up. Okay? If that potential goes up, it says that everybody flowing into that node is going to flow a little less in, right? Because the voltage just went up. So you flow a little less in. And by the way, the outflows from that node are also going to increment a little bit. Because if you pull the voltage on a node up a little bit, the outflows are going to increase a little bit. But if the inflows go down a little bit and the outflows go up a little bit, it says that the total, if that node was oversubscribed before, too much net current, then that's actually going to be a correcting move. So, and the point is just that these are embarrassingly simple to write down here. So these are not algorithms you couldn't figure out or make up intuitively, but the nice part is now you know exactly what they are and how they work. So that's it. So it's really embarrassingly simple. Okay. Well, as I said, it's completely decentralized and so on. And you get flow conservation only in the limit here. And once again, the same story holds. If you decide to actually run the flows, if this is not just a discussion among edges and flows and adjusting potentials before you actually turn on the flows, if the flows are actually running, if you have a residual at a node for that step, it increments or decrements a buffer. And that in an electrical network, that would be you'd have capacitors at the edges. And if there's too much flow for an iteration, no problem. The charge on that capacitor just increments up. It can also be warehouses where you're storing things, or buffers in a network or something like it could be warehouses. If too much stuff went in at that step, all it does is pop up the queue length, for example. By the way, if too much stuff flowed out, that's capital SI negative, your buffer actually dropped down a bit. So that's the picture. Okay. It's probably not a bad idea to explain fully all this, although I think I've said a lot of this. This is related to an electrical network. And this is only for people who know about electrical engineering. So if you don't, that's fine. Let's see. So here, the variable is the current. These are the currents in the branch. The source is an external current injected at that node, and they have to sum to 0. Otherwise, there's no solution of AX plus S equals 0. I guess that's kind of obvious. The flow, this AX equals S. Wait a minute. Did I just all of a sudden reverse the sign on S? I think I did, didn't I? Wasn't it AX plus S before? Do you mind? Let me just write that AX plus S equals 0. And then we have to figure out if that's injected or pulled out. It's one or the other. And then we'll make it 0. Just for aesthetics. The dual variables correspond to node potentials. And then these are the branch voltages. Of course, in electrical engineering, you know that in anywhere, physics or electrical engineering, if you say potential, by implication, that's a quantity where differences matter, not the absolute values, unless you have some reference or datum value, a ground potential. That's the same thing here. And the branch current voltage characteristic is exactly this thing, which is the inverse of the derivative of that function. And what I could mention here is the following. If the flow if the local flow cost functions are quadratic, then it turns out this is linear. That's obvious, right? Because then the derivative is a linear function. The inverse of a linear function is linear. Okay, so in fact, this goes back to 18. I won't get it right now, but this goes back to Maxwell, who announced that an electrical network, if you have a bunch of flows in a network, in a linear resistor network, the currents arrange themselves in such a way as to minimize the total energy in the network. Okay? When they are minimizing total energy in the network, then almost by accident, or I don't know how you want to say it, you will get flow conservation. That's the other view of electrical engineering. The more primary view is to say, no, there's flow conservation, or something like that. But it turns out it's a minimization problem. So, okay, so that's it. Okay, so let's look at an example. It's going to be minimum queuing delay on a single commodity network. So the flow cost function is going to be something like this. It's going to be xj over c minus xj. And this is something like roughly a queuing delay. I mean, it doesn't matter, right? I mean, but it's roughly a queuing delay. And you can see here that it's got a capacity, and as you run the traffic up to the capacity, what's going to happen is this denominator is going to get very small, and your queuing delay is going to get very large. So this is that. On the other hand, if you lightly load it, you're going to get a very small queuing delay here. So this is the queuing delay. And that's, of course, a convex function. And the conjugate of this, you can just work it out. It's not very hard at all to work out the conjugate of that convex function. And it turns out to be this. It's the square root of cjy minus 1 squared over some range and so on. Actually, I think we have some plots of these. So here are some plots. Here's the queuing delay. It says if you lightly load the network, then the queuing delay on that edge is going to be small. It's going to increase rapidly as you approach this is for a queuing, this is with c equals 1. As you approach the capacity, your queuing delay is going to go nuts, like this. And the conjugate looks like this. It's 0 out here, and then it goes up this way. Okay, so that's the conjugate. Okay, so this is the mapping from potential difference to, you take the inverse of that function before, and you get exactly this. It's the mapping from a potential difference to a flow, something like that. By the way, the potential differences here are actually going to be kind of interesting. If you think of we'll be able to see that this analogy is going to work beautifully because if we measure the potential, if you set everything upright and scale time properly, you get the following. Your dual variables are actually going to be the queue lengths at the nodes. You're going to have a queue at the node. And what's going to happen is you're going to look at the difference in the queue lengths. That's called the back pressure. And for example, and then you're going to flow depending on the back pressure. And in fact, this is going to tell you how much to flow, like that. So that's the way this is going to work. Okay, so here's just a little baby example. You have 5 nodes and some link and some all the capacities are 1 here, and it's a single commodity network. And I don't see where the input and output is. I believe the input's supposed to come in here, and it's supposed to go out there. But it's interesting that it doesn't say it here. Oh, I guess it doesn't have to say it, does it? Because those are the S's or something. So I guess that's fair. So here's the optimal flow. So these are given. That's an input. So stuff is pumped into the network here, and it's pumped in here, and it's pulled out here. This obviously is the sum of these two. So you'd call it a data collection network or whatever you want. By the way, we're minimizing the sum of the queuing delays on the network, and basically that's actually the number of packets in the network, roughly. So that's what we're. No, sorry, it's not. No, sorry, there's multiple. I take that back. It's not that. It's the average queuing delay. So, okay. So let's take a look at what happens. It says that what comes in here. I guess this is equal to. I don't know why that doesn't somehow this should have the same width as that. I don't know why. That's very interesting. Wow, these are weird. It's all spooky. Yes. We can just ignore it. It's weird, right? It's obviously wrong. I mean, the only thing I'm concerned about here is the width of the, I guess, the intention is that the width of the arrow shows you the flow level. But I think if you look at this, I'm getting some real bad, I'm getting kind of a KCL headache here because that does not look good, okay? And this doesn't look good, and because the sum of the width of this and this, I think, is probably that. And that goes here. So I'm not quite sure what we're seeing here. I'm going to have to think about this, and we'll examine this and figure it out. But maybe it has an explanation. I'm just confused right now. But anyway, okay. So this is the optimal flow, and in particular on these cross links, there's zero flow. What's shown here, these are the potentials. For simplicity, I could add any number I like 5 to all of the potentials. It would make no difference whatsoever. But I just took the termination node and made that the zero or the ground potential. So these are the potentials here. And then you can look at the potential difference. Maybe that is the difference between that and that. Well, who knows? It could be, is it? Can you eyeball them? Anyway, what is it? It is, okay. So maybe this tells you the potential difference or something like that. The width of this is supposed to give you the flow level, but that's deeply suspicious because, for example, this thing is way too small or something here. So we'll have to figure out what actually happened here. Okay, but that's the picture. And then here's how this would actually here's how this would run if you did this. What you do is the following. This is just showing for several different step sizes here, a constant. So here you just initialize all the potentials to 1 or whatever, and you get all sorts of flow errors or something like that. And what happens is this: if you have if you take alpha is 0.3, this dual function shoots up and approaches what is the optimal one pretty quickly. 1 maybe goes up more quickly or something like that. Actually, maybe this is the 0.3. That's 1 and that's 3. I got it all backwards. I should have just read the legend anyway. So 0.3 is a nice slow step size. It's going to go up to the optimum. 1 is maybe the optimal step size, and 3 is so much that you're actually oscillating a little bit, and you're not going to converge to the actual solution here. You're going to converge to a neighborhood of it or something like that. So this is the picture. Oh, and 2.48 is going to be the optimal flow. Okay. Primal residual is going to be the norm of the flow error, and you can see things like you can see it go down and stuff like that with the different things. This one is not converging. Is going to converge merely to a neighborhood of the solution, and so it's probably not going to get any better than that. So that's the picture here. And here is the convergence of the potentials to their optimal values. I guess there's 5 nodes. One of them has potential 0, so we don't plot it. And this just shows how the other ones are going. And this is for the step size of 1 rule. And this shows the potentials going, converging to their optimal values. Okay, so that finishes up these 2 applications. Let me just mention a couple of things. If you study these and get a feel for them, you will be able to construct and solve problems that are, much more complicated. And let me just mention a couple of examples. Let's do multi-commodity flow. So in multi-commodity flow, it's the same as a single commodity flow problem, where you can have flows splitting and all sorts of other stuff, except you have different flows. They are completely separate. They are coupled by the costs on the edges, right? Which could just be capacity costs, but they're coupled by the costs on the edges. Everybody see what I'm saying? So basically you have the same trucks that take material from one place to another, but you have multiple products. And the number of trucks you use to send stuff from one warehouse to another doesn't matter. I mean, it's how much of what the product mix in that truck is doesn't make any difference. It's the same price. And so you have the multiple flows. That's one. I mean, you can go on and on. A common one in networks is that would convert both of these would be something like this. Instead of having a fixed route, from source to destination. That's our first problem. You would have 10 good routes. So 10 good routes. And you're allowed to split across those 10 routes. So that's a common setting that's in between these two. Everybody see what that is? So for each source destination pair, you have 10 things. You have 10. You can split the flows across them. So it's not like the single commodity flow where you can completely split at every node the flows and then recombine them. This allows you to pump your traffic along 10 different routes or along any divisible combination of 10 different routes. So that's that one. Okay, so I think we'll quit here and we'll start a new section of the class. Next time, actually, I have some questions for you. We haven't quite decided what we're going to do next. And let me tell you what some of the options are. Maybe you have an opinion. They might have to do with your projects, but it's up to you. So one option is that we can jump on to these methods for solving extremely large problems, like 1 million variables and more. That's option one. It's very interesting material. That's one option. The other option is that we can do some applications that we've just worked on, like sequential convex programming. That's for non-convex problems. Is that a vote? Okay, we're getting a vote for that. 2. Okay, well, 3, 4. How about solving the super large problems with truncated? Ooh, ow, yikes! Don't worry because they're not. It's only going to matter by a week. Wow, that was very close. You know what? I'm very sorry to say this, but we may have to wait until the convention to decide. So that's what we're going to do. But let's try the hands one more time. Super delegates for sequential convex programming, please.
There's only 2 options.
What?
Only 2 options right now. You only gave us 2 options.
Yeah. Do you want me to do? I'll do something else. What do you want me to do?
Oh, I was just wondering if there were more options before.
Yeah, we got other options.
Okay.
But these it seem to us are the ones that are going to be useful to you, like very soon. Okay. Sequential convex programming is like, oh no, I knew it. It's just totally split. I'm not going to be reduced to counting. Okay, I will. 1, 2, 3, 4. I just sampled. Okay. How about? And the other one was the super large problems. Oh God. Oh, okay. That might have had a slight edge. So anyway, the super delegates will confer this weekend and decide in private, in back rooms, what's going to happen, and then we'll move forward.